Let's take a look at bar charts and pie charts from what we looked at from our in-class day. So we're going to extend on that a little. So we're going to look at creating, reading, and some things that make graphs a little misleading. All right, so first of all, when do we create bar or pie charts? Well, we have to go back to qualitative versus quantitative data. So do you remember when we talked about qualitative versus quantitative observations? Whenever we have something that's quantitative, that is something that is quantities. I think they both have the word quant in them. Things like measuring height, weight, distance, time, they're all numerical measurements, and those are considered quantitative observations. Qualitative observations are qualities, and those are things like maybe color, favorite food, favorite class, type of pet, and those are all things that can be put into categories. Those are considered qualitative observations. So, whenever we have qualitative measurements that can fit into categories, that's what we use bar and pie charts to display. So let's do an example. Let's say I have a class of students and I'm trying to collect data on hair color. So I ask all of my students, you can see all 12 of them there, say, what color hair do you have? Well, I can summarize that data into a table. So the first thing I would do is break up the categories. Okay, so how many people have brown hair? I have 5 in that category. And how many people have blonde hair? I have 3 in that category. Same with black hair. I have 3 people in that category and 1 person with green hair. So in my table, I can display hair color and the number of students with each corresponding hair color. So there are my 5 students with brown hair, 3 with blonde, 3 with black, and 1 with green. And at the bottom of the table, I can put the total, which is 12 students. So I can take this data, and it's not necessarily very useful in a table, but we can create a display that shows what this data is communicating. So let's create a graph. Well, one graph that we could create that we looked at is a bar graph. So on the x-axis, we have hair color, and on the y-axis, we have the number of students. And each bar reaches up to the number of students. So for example, there are 5 students with brown hair, and that bar goes up to the number 5. We also have to be sure to include a title that displays and communicates what we are looking at. So we are looking at hair color of students in physical science, and my x-axis is labeled my categories with hair color and the number of students on the Y. So I can look at the graph and tell me exactly how many students are in each category and what that is saying. Notice how my scale starts at 0. It is really important that when you create a bar graph, your scale starts at 0. Also notice how this graph fills the page up very nicely. There's not a whole lot of extra space, which sometimes it happens if you have one really large bar and really small ones. But you want to take up as much of the space as possible. So how is a pie chart different? Well, pie charts use percentages. So if we go back to the bar chart, you can see that the bars communicate the actual number of students. So I can see I have exactly 5 students with brown hair. So a pie chart is going to show the percent of students. And what that does is it makes it easy to compare data. Because if I'm comparing a group of 10 students to a group of 25 students, it would be helpful to know the percent. It's also easy to compare within a set of data if we have percentages. So it makes it easy to compare each individual group to the whole entire group. So how we calculate percent is we take the part divided by the whole, and then we multiply it by 100. So if we look in the column that says percent of students calculation, what we can see in this column. So let's take a look right here. If we're trying to find the percent of students with brown hair, we would start by taking the part. So that would be 5, and then we're going to divide that by the whole, which is 12. So we take 5 divided by 12, and we multiply it by 100, and that gives us 42%. If I'm doing the number of students with blonde hair, I take the 3 students divided by the 12 total, and then multiply it by 100 for a total of 25%. Notice that the students with black hair, they have the same number in each group, so both of them have 3 students, so they're going to have the same percentages. So then the number of students with green hair, that's 1 out of 12, so 1 divided by 12 and then multiplied by 100 gets us to 8%. So one thing that's really important is that our categories add up to 100%. We're missing information if our categories do not add up to 100%. And we did a wrong calculation if we have over 100%. Every once in a while, with rounding error, you might get 99%, and that might just be because you rounded something incorrectly. So again, make sure that your percentages add up to 100. So we can display that data into a pie chart. And what you will notice is pie chart still has a title that describes what we're looking at. So we're looking at the hair color of physical science students. And it has a key to show us what color represents what hair color. So by looking at this pie chart, we can see the biggest slice is people with brown hair, and that's 42%. So 42% is just a little below half. Half is 50%. And so we can see that this slice takes up almost half of the circle. If we look at the two 25% here, 25% is 1/4. So each slice here takes up 1/4. And then we have the remaining 8% with the green hair. So again, this is easy to compare within the group. The largest group is the students with brown hair, and we can see the blonde hair and black-haired students are the same size. We have to talk about some graphs that are misleading. So the biggest thing that you should look for is a scale that doesn't start at 0. It makes data comparison look a lot more drastic than it actually is. So let's look at an example. Here I am looking at an average class score. And by looking at that graph, I can compare Mr. Jones to Miss Smith. And I can see the average class score along the y-axis. So Mr. Jones's average is 73.2 and Miss Smith's is 74%. So just by looking at this piece of the graph, it looks like Miss Smith has a much higher average than Mr. Jones. Almost 4 times as large. Okay, it looks like there's a very big difference between those two teachers and their average class score. But take a look at your scale. The scale starts at 73. It doesn't start at 0. So if we actually look at that same data, but we put our scale at 0, now it looks like Mr. Jones and Miss Smith have pretty much the same average class score. So a lot of times when people want to show a really big difference, they will make sure that they only focus on one part of the graph and their scale won't start at 0. So here, one starts at 0, the other starts at 73. And if we focus just on the top of those bars, cut the rest of the graph off, we can make it look like there's a very big difference. So those are misleading graphs. They're inaccurate and we should not use them. Other misleading graphs are when we have a persuasive title. Your graph title shouldn't tell you how to think. It should just tell you what's displayed. So this one says, massive increase in home price. Well, it's really up to the reader to decide if it's a massive increase. It really should just say, home price in different years so that we can look and compare the average home price in 1998 to 1999. Also, if we have too much empty space on a graph, that is misleading because we can't really get a good picture. Notice how everything is squished in that tiny little area. So it's important to create our scale so that we can see our data clearly and that we don't have too much empty space. And then if we don't have any title or axes labels. So here we have this graph and it's a line connecting these different dots, but we have no idea what this graph is showing. Is it showing time? Is it showing distance, age, money? We don't know. So graphs that don't have a title or any X or Y axes labels, those are misleading graphs. And all these are types of graphs that we should not use.